So this lecture is on complex numbers, and complex numbers occur when you have to take the square root of a negative number. So square root of a negative number is not real, it is imaginary. So square root of negative 1 is what we denote as I, and that is a complex number. So anytime you see a square root, or even a fourth root, or an even root with a negative number, you have to be cautious. So I have square root of negative 25. I could write that as square root of negative 1 times 25. And we know we could split the roots and write it as square root of negative 1 times square root of 25. Square root of negative 1 is I, and square root of 25 is 5. So we have plus or minus, because we are taking the square root. So the answer is plus or minus 5i, or I5. It doesn't matter how you write it, but typically we write it as I times 5. I comes in the front. So the next problem we have square root of negative 32. I could write that as square root of negative 1 times 2 times 16. You may ask me, well, why are they writing it this way? Because I'm trying to get a perfect square of some sort, and 16 is a perfect square. So we can split it up and write it as square root of negative 1 times square root of 2 times square root of 16. Square root of negative 1 is I. There is nothing we could do about square root of 2. We'd leave that as is. Square root of 16 is 4. So we could write it as I 4 square root of 2 and plus or minus in the front. Same applies here. I could write this as negative 1 times 121. 121 is a perfect square to begin with, so we could split it up and write it as square root of negative 1 times square root of 121. So we have I times 11 and plus or minus. Oftentimes you may encounter scenarios such as this one, and you may say, oh, I see a negative number inside a root, negative number inside the other root, so certainly there has to be an imaginary number. But if we have separate terms, one thing to do is to combine and see if the negative goes away. So I'd have negative 3 times negative 5, which is square root of negative times negative is positive, and I'll have positive square root of 15, which is a real number. There is nothing we have to do about it now. So here we have one number divided by another, and both of them are with inside roots. So I'm going to combine the roots first. Divide and see what happens. So negative 125 would be negative 25, which is square root of negative 1 times 25. We can split it up and write it as square root of negative 1 times square root of 25. And square root of negative 1 is I. Square root of 25 is 5. So we have plus or minus I times 5. So what we saw, they're all complex numbers, or most of them, because they had I. But there is what we call a general form of a complex number. And that general form is A plus B times I. So A is a real number, and B by itself is also a real number. So that is real b is a real number, but b times I put together is a complex number. And when you add it to a, that entire thing would become a complex number. So, of course, if you plug in b equals 0, that term would become 0. You simply get a. And a, I said, is a real number, so the resulting answer is real. So if the imaginary part is 0, then you get a real number. So what do I mean by the imaginary part? We have a plus bi. The first number is what we call the real part of the imaginary number. The second is the imaginary part of the imaginary number. So, on the other hand, if a is 0, we end up getting b times I, and b times I is an imaginary number because there is I there. Now we move on to adding and subtracting complex numbers. So the key here is to combine real parts, combine imaginary parts, simplify, and you get the result. An important thing to notice here is just because you are adding complex numbers doesn't imply, or adding or subtracting complex numbers doesn't imply the answer would always be a complex number. So you've got to note the result could either be real or complex. So don't forget that. So here we have some examples in adding and subtracting complex numbers. So first step, I'm going to write it as 4 plus 6i plus 3 minus 2i. Combine the real parts, which would be 4, 3. Put an I and combine the imaginary parts, 6, negative 2. 4 plus 3 is 7. 6 minus 2 is 4. We have 7 plus I times 4, or 4i. So it's entirely up to you. So you can either write it that way, or you can write it as 7 plus 4i. So here we have 8 plus 2i minus 4i. And you may say, oh, there is no real part here, and it might lead to confusion, but I can write that 4i as 0 plus 4i. So I can combine the real parts. There is a let me expand this out. So we have 8 plus 2i minus 0 minus 4i. I can combine the real parts, put an I, and I'll combine the imaginary parts, just the coefficients. So I have 8, 0, and there is a minus. 8 minus 0. 2, negative 4. 2 minus 4. 8 minus 0 is 8. And I times negative 2, which is 8 minus 2i. Multiplying complex numbers is pretty much the same as how we would multiply, say, an expression with two factors. we are going to FOIL, and we would end up getting an expression which we would simplify to get the final answer. Now, key thing to notice here is that I squared is equal to -1. That would help us in simplifying the final expression. And keep in mind again, the result could either be complex or imaginary. So just because you're multiplying two complex numbers doesn't imply that you are going to get only a complex number as the answer. The answer could either be real or it could be complex. So let's multiply these two simple terms. So I'm going to bring all the numbers together. So 8 times 7, and the i's together, I times I. There are two i's, so we've got to account for both of them. 8 times 7 is 56. I times I is I squared, and I squared is -1. So the answer is -56. Here is an example where we have 5i on the outside and a full complex number on the inside of the parentheses. So we are going to first distribute, so 5i times 4 minus 5i times 7i. 5 times 4 is 20, so we have 20i minus 5 times 7 times I times I. I times I is -1 because I squared is -1. So we have 20i plus 35. So the answer is 35 plus 20i. You may leave it as is, or you could take out the common factor, which is 5. So if 5 comes out of 35, we have 7. And if 5 comes out of 20, we have 4i. So this is the case where we have to distribute or FOIL and simplify. So if I use typical foiling, I have 6 times 7 minus 3i times 4i minus 3i times 7 plus 6 times 4i. 6 times 7 is 42. 4 times 3 is 12. I times I is I squared. 7 times 3 is 21, and there is an I. 6 times 4 is 24, and there is an I. So 42 minus I squared is -1. 24i minus 21i is 3i. 42. -12 times -1 is +12. Excuse me. Minus 3i. We have 54 minus 3i. We can simplify this because we have 3 as a common factor. So if I pull 3 out, I have 18, or 3 times 18 minus I. So dividing complex numbers requires a nice little trick, and that trick is called conjugation. So if we have a complex number, a plus I or a plus bi, its conjugate is a minus bi. Likewise, for a minus bi, its conjugate is a plus bi. And when we multiply a complex number, by the conjugate of the complex number, the result is always a squared plus b squared. In other words, complex number multiplied by its conjugate would always equal to the real part squared plus imaginary part squared. So we have to use the concept of conjugation to divide two complex numbers. So anytime we divide complex numbers, the first thing that has to come to your mind is a complex conjugate. This is very similar to rationalizing radical functions when we divide radical expressions. So the objective is to try to get rid of So the objective is to get rid of a complex number in the denominator by converting it to a real number. How do we do that? So we have 6 plus 2i divided by 4 minus 3i. Now with radical expressions, we can rationalize the denominator. In other words, we could get rid of the radical in the denominator by multiplying and dividing by its conjugate. We are going to do the same thing. We will multiply and divide by the conjugate of 4 minus 3i in the denominator. So we have 4 plus 3i divided by 4 plus 3i. So now, in the denominator, we have a complex number multiplied by its conjugate. Complex number, conjugate. And what do we know about that from the previous explanation? If we multiply a complex number by its conjugate, all we have to do is to square the real part, square the imaginary part of the complex number, and add. So the denominator is easy here. It's simply real part squared, imaginary part squared, 16 plus 9, we end up getting 25. The numerator we are multiplying 6 plus 2i by 4 plus 3i. We distribute and will FOIL, so we have 24 plus 6 times 3i plus 2i times 4 plus 2i times 3i. 6 times 4 is 24. 6 times 3i is 18i. 4 times 2i is 8i. 3 times 2 is 6. I times I is I squared. So we have 24 plus 36i plus 6 times negative 1. So we have 24 plus 36i minus 6, which is 18 plus 36i. So the numerator is 18 plus 36i, the denominator is 25, so our result is the numerator divided by the denominator. Since we have a common denominator, we could write it as 18 over 25 plus I times 36 over 25. So the final result is a complex number, and the real part of that complex number is 18 over 25. The imaginary part is 36 over 25. This is a division problem, but it is simple compared to the previous one. So you may say, well, there is no real part in the denominator, so how do I find the conjugate? So I could write 6i as 0 plus 6i. Now we can identify the conjugate, which is simply 0 minus 6i. In the denominator, we have a complex number multiplied by its conjugate. So the answer is simply the real part squared plus the imaginary part squared. So we have 0 plus 36. The answer is 36. The numerator, we have 5 times 0 minus 6i. Distribute, we have 5 times 0, which is 0. 5 times negative 6i is negative 30i. So the result is the numerator, negative 30i, divided by the denominator, which is 36. We can simplify this further because there is a common factor between 30 and 36, which would be 6. So we have negative 5 over 6i. Complex numbers have a very interesting property just by I. It has a very nice pattern when we raise it to the power of I. We know I squared is negative 1. Do not forget that. So, which would also mean that I is the square root of negative 1. Which is what we have there. Now, I cube, I could write it as I squared times I. So, but I know that I squared is negative 1, so I cubed would simply be negative I raised 4 is I squared times I squared, but we know I squared is negative 1, so we have negative 1 times negative 1, we get 1. Then I raised 5 would simply be I raised 4 times I, but we know I raised 4 is one. So you take that 1 and plug it in there. We have 1 times I, we have I. And use the same process to write I raised 6 in terms of the previous powers. So we have I raised 4 times I squared, and we have I raised 4 to be 1, I squared is -1, 1 times -1 is -1. So I'm going to write this out. So if we start, we have I minus 1 minus I 1, and we have I minus 1 minus I 1. So that's 1 through 4. That would be powers 5 through 8. And you can see that those two blocks are identical. In the sense you have I minus 1 minus I1, then you have I minus 1 minus I1. So naturally, I could just keep on going. The next one would be I minus 1 minus I1, I minus 1 minus I1, and that block would be powers 9 through 12, and that block would be powers 13 through 16. So there is a cycle here, and what is that cycle? And that cycle is simply I raised 4k equals 1. In other words, if we know the first 4, then eventually we could find the rest of them easily. So here we have I raised 53. Now, could I write that as a multiple of, could I write 53 as a multiple of 4? So I could write it as I raised 52 times I raised 1. The bases are identical. When I add the powers, 52 plus 1 is 53. I raised 52 is simply I raised 13 times 4, and that's just I. Now, using rule of exponents, I could write this as I raised 13 raised 4 times I. The next question is, well, could I write I raised 13 as a power of 4? Well, before we go to that, what would I raised 13 equal to? We would have I raised 4 times 3 plus 1 raised 4 times I, which is I raised 4 times 3 times I raised 4 times I. What is I raised 4? We know I raised 4 is 1. So you have I raised 4 raised to the power of 3 times I raised to the power of 4 times I. So that would be 1 cubed times I raised 4 times I, which is simply I raised 4 times I. I raised 4 is 1, 1 times I is I. You may say, well, that is quite long. Well, it is long because I try to simplify it in extremely lower terms of I raised 4. Could I have done it a different way? So at the very first step, I could have realized that instead of writing I raised 52 as I raised 13 raised 4, I could have written it as I raised 4 raised 13 times I. But what is I raised 4? I raised 4 is simply 1. So we have 1 raised 13 multiplied by I. 1 raised to any power is simply 1, so end up getting the same answer, I. So you just have to be careful and think about the problem first. I showed you 2 different approaches. One, the lengthy way, you're trying to write it in simple powers of 4. The other is the easier way. So here we have a negative exponent. Now, some people are quite comfortable with negative exponents, but here we have a trick that the complex number would recycle through powers of, or powers that are multiples of 4, as I minus 1 minus I and 1. So to use that, I'm going to rewrite I raised negative 17 as 1 over I raised 17, which would equal to 1 over I raised 16 plus 1. You may ask me, why is he writing it as 16 plus 1? I'm doing so because 16 is a multiple of 4. If I have a multiple of 4, I can express it, or I could go back to the patterns over there and pick an answer easily. So 1 over I raised 16 times I. I could write I raised 16 as I raised 4 raised to the power of 4. I raised 4 is positive 1 raised 4 times I, so we have 1 over I. And we shouldn't leave it as 1 over I, because that is not the proper representation of a complex number. So we have I raised negative 17 to be equal to 1 over I. How do we simplify it and put it in the right form? We multiply and divide by the conjugate. So I could rewrite I as 0 plus I. Therefore, its conjugate would be 0 minus I divided by 0 minus I, or I multiply and divide by the conjugate. So in the numerator, we have 1 times 0 minus I. In the denominator, we have 0 plus I times 0 minus I. Distribute 1 in the numerator. 1 times 0 is 0. 1 times negative I is negative I. In the denominator, if we FOIL, we have 0 plus 0 plus 0 minus I squared. But what do we know about I squared? I squared is negative 1. So we have negative I over bad algebra 1. So the answer is negative I.